This topic is investigating graphs of polynomial functions. So there are 5 graphs below of polynomial functions, and the first graph shows you a linear function. The degree is 1, so you're graphing a line. When the degree is 2, you're graphing a quadratic function. A degree of 3 is a cubic function. Degree of 4 is a quartic function. And our last one, degree of 5, is a quintic function. So you do need to know the degree and the name of the function. So I'm just going to go ahead and write y equals x, y equals x squared, y equals x cubed, y equals x to the 4th, and y equals x to the 5th. End behavior is going to be used to graph polynomial functions. So there's a table here that shows you the end behavior of 4 graphs. When the degree is odd, the end behavior is going to be opposite direction. So here are 2 examples of odd degree polynomials. Notice it is rising on the right side and then falling on the left. And that is when the leading coefficient is greater than 0 or a positive number. The second one is it's rising on the left side and then it's falling on the right side, and that's when the leading coefficient is a negative or less than 0. The other scenario is when you have even degree polynomials. They are going to have the same direction. So we have 2 more graphs with even polynomials. Here are 2 quadratic graphs. Notice it's rising on the right and it's rising on the left. And that's when your a is greater than 0 or a positive number. The second one is it's falling on the right and it's falling on the left. And that's when the leading coefficient is less than 0 or a negative. The next thing is called a turning point. A turning point is where a graph changes from increasing to decreasing or vice versa. So the graph increases and then it turns to decrease, or it decreases and then increases. These are where we're going to have local maximum or minimums. So this would be a local max, and then this would be a local min. We have an expression that we can use to determine how many turning points we have. So n represents the degree, and we substitute it into this expression n minus 1 to find out how many turning points there are. Example 1, identify the leading coefficient, the degree, the number of turning points, and the end behavior, and then sketch a graph. So here's our polynomial, and we want to first identify the leading coefficient. So that's the number in front of the x to the 4th power. So that's your LC, your leading coefficient, and that number is -1. So your leading coefficient is -1. The next thing is we identify the degree. That is 4. So we're going to have a quartic function. Then we identify the end behavior. So the end behavior is based off the degree. So the degree is 4, so it's even. And then the leading coefficient is a negative. So that was a -1. So what's going to happen is our quartic function is going to fall on both sides. So it's going to fall on the right and it's going to fall on the left. So both sides will be down. And the reason why is our A is less than 0, so our leading coefficient is less than 0, and our degree is even. So that means both sides will go down. The next thing is the number of turning points we have. So we use our expression n minus 1. Our degree was 4, so 4 minus 1 is 3. So we have 3 turning points. Then we're going to go ahead and sketch just a little sketch of our graph. So here is our y-axis and our x-axis. And we first do our end behavior. So this is telling us it's falling on the left and it's falling on the right. So both sides are falling. And then we have essentially 3 turning points. So it's going to rise and fall and rise and fall. So we have some type of maximum here. I don't know what it is, how high it is. It's just a sketch. I have some type of minimum here. I don't know where it is. And then I have another maximum. And what we'll do later on in our chapter is we will find out where those maximum minimums occur. But this is just a sketch. Example 2. Identify the leading coefficient, degree, and the number of turning points and end behavior. So we look at our 2, that is our leading coefficient. So our leading coefficient is a positive number. So we're at this scenario right here. Then our degree is 5. So we have a quintic function. And that degree is odd. Now we want to identify the end behavior. So since the degree is odd, we're going to look at the first column. And then our leading coefficient is positive. So what happens is we are rising on the right and falling on the left. And that's because our leading coefficient is greater than 0 and our degree is odd. Then we want to identify the number of turning points, n minus 1. So n represents the degree, so it's 5, minus 1 is 4, so we have 4 turning points. Now we're just going to do a sketch. So we know we're going to rise on the right side and then fall on the left side. So that's the end behavior. And then we have 4 turning points. So that means we're going to have to rise, fall, rise, fall, rise. And then we count our turning points. 1, 2, 3, 4. Now, do we know what those points are? No. We will find that out later on in our chapter. So those will be our local maximum and minimum points. Here's that table again. Example 3 now says, identify whether the function is odd or even, and if it has positive or negative leading coefficient. So the first graph shows that it's rising on the left and it's falling on the right. So we know then that this is going to be an odd function because they both don't go up or both don't go down. So we know for sure it's going to be odd. And then notice that it's rising on the left and falling on the right. So our leading coefficient will be a negative. Second example, notice that both sides are going up. So the right side is going up, so it's up on the right, it's up on the left, so both are going up, so this is going to be an even degree. And then that tells us then that our leading coefficient has to be a positive number. Has to be greater than 0 for both sides to go up.